Hi students, welcome to my channel Thoughts of Physics.
In the video series of moving charges and magnetism, in this class I am going to explain the magnetic force on a current carrying conductor. So current carrying conductor, when the current carrying conductor is placed in the magnetic field, it experiences a force, magnetic force. So the magnetic force experienced by a current carrying conductor. So let us consider a current carrying conductor, that may be a conducting rod or a conducting wire. So the length of the rod, let us say L. L is the length of the conducting rod or conducting wire, and A is the area of cross section, uniform area of cross section A. And this conducting rod or straight wire, let us say the conductor. The conductor is placed in the uniform external magnetic field. Already magnetic field established, and in that magnetic field this conductor is placed. The length of the conductor is L, capital A is the area of cross section. And now let us say small n is the number density, that means number of charge carriers per unit volume. Charge carriers means generally in metallic conductor free electrons are the charge carriers. So small n is the number of free electrons per unit volume. Now total number of charge carriers in that conductor, that gives small n into AL, because A into L, area into length, is the volume of the conductor. A into L is the volume of the conductor. Per unit volume, number of free electrons, small n. So the total volume AL, the number of free electrons becomes n into AL. So n into AL is the total number of charge carriers or total number of free electrons in the conductor. So let small q is the charge of each electron, free electron. Small q is the charge of each carrier. Now the total charge means total number of charge carriers into the charge of each carrier. That means q, that is the q is the charge of each charge carrier, and n into AL is the total number of charge carriers. So it gives q into NAL, it gives total charge of the conductor, total charge of the conductor. So when a steady current I flows in this conductor, each charge carrier has an average drift velocity. Already we have discussed the concept drift velocity. Whenever electric field is established, in that electric field, in the presence of electric field, charge carriers moves with an average velocity called drift velocity. When I current flows, each charge carriers travel with a velocity Vd. Vd is the drift velocity. Now, in the presence of external magnetic field B bar, the force experienced by the charge, already we have discussed the force experienced by the positive charge. So we have discussed in the last class, that is F bar is equal to Q into V bar cross B bar. This is the charge Q, total charge. V bar is the velocity. When the charge is moving with the velocity V in the magnetic field B, the charge experiences a magnetic force. F is equal to Q into V bar cross P bar. Here Q is the total charge of the conductor here. Now already we have obtained the expression for the total charge of the conductor, Q N A L. This is the total charge. So in place of Q I am writing the total charge. So Q means we have written this for one charge carrier. So this in that conductor, so these many number of charge carriers are there, NAL, total number of charge carriers. Each charge carrier having a charge small q. So this will be the total charge. So this is the total charge, and V becomes Vd, because in the presence of electric field, whenever current flows, what happens means all the electrons move with average velocity Vd bar. Then Vd bar is the velocity cross B bar. This is the force experienced by the conductor, magnetic force experienced by the conductor in the presence of magnetic field. So now that is equation number 1. So now already we have discussed that relation between current and drift velocity. The relation between current and drift velocity is I is equal to NEA Vd. So where small n, that is the number density, number of charge carriers per unit volume. E is the charge of electron. Capital A is the area of cross section. Vd is the drift velocity. Now here this formula we have taken small e is the charge of electron. Here we have taken charge of the charge carrier is q. So that's why this formula can be taken as I is equal to n. In place of small e, just we have taken q. That's it. NQAVD. This is the current I. So in the equation number 1, if you observe NQAVD. So in place of this NQAVD, we can write I. If you write I in place of NQAVD, we left with here L into I. That will get I into L into, that is B. We left with only the three quantities. The current I in place of Q, N, A, V, D, we have I and L and B. So but electric current is not the vector quantity. Electric current is not the vector quantity. So the vector transformation is shifted to the length L bar. So that's why the force experienced by the conductor finally F bar is equal to I into L bar cross B bar, where L bar is the length of the conductor, B bar is the external magnetic field. So F bar is equal to I into L bar cross B bar. This is the force experienced by the conductor in the external magnetic field. Now, so the direction of this F bar, already we have discussed that it is the vector product of L bar and B bar. In case of vector product, the force F bar is perpendicular to L bar and perpendicular to B bar, both L bar and B bar. So if L bar and B bar present in one particular direction and F bar is perpendicular to both these L bar and B bar. L bar and B bar are in the plane means, and F bar is perpendicular to the plane. That is, F bar is perpendicular to L bar and B bar, and the direction of this force is given by the right hand thumb rule or right hand screw rule. In the last class we have discussed what is right hand thumb rule and what is right hand screw rule. And the magnitude of this force can be given by F is equal to, if you apply the formula of cross product here, L bar cross B bar is L into B into sine theta. The magnitude of L bar is L, the magnitude of B bar is B, and cross product is sine theta. That is, L bar cross B bar is equal to LB sine theta. So finally we will get the magnitude of the force F is equal to BIL sine theta. This is the magnitude of the force experienced by the conductor placed in the external magnetic field. Now here the theta is angle between L bar and B bar. Here the cross product. The angle between L bar and B bar is theta. Now the force is 0. Now F becomes 0. If theta is equal to 0, sine 0 is 0, then force becomes 0. So theta is equal to 0 means, and L bar and B bar both are parallel or anti-parallel. Both are in the same direction. That means in the direction of L bar, the conductor placed in the direction of magnetic field. The conductor is placed in the direction of magnetic field, parallel or anti-parallel, then the force becomes 0. That means when the conductor is placed in the magnetic field, in the direction of magnetic field, it doesn't experience any force. The force is maximum if theta is equal to 90 degrees. Theta is equal to 90 degrees means when the conductor is perpendicular to the magnetic field. L bar means the length of the conductor. So when the conductor is perpendicular to the magnetic field, then it experiences the maximum force. The maximum force is given by here sine 90. Sine 90 is 1. So now F is equal to BIL. This is the maximum force experienced by the conductor when it is placed in the magnetic field. Now actually, so this formula whatever we have discussed here, that is F bar is equal to I into L bar cross B bar, or the magnitude is F is equal to BIL sine theta. This formula holds good only for a straight conductor. When the conductor is straight, then only this formula is applicable. It holds good perfectly. So for example, if the conductor having any arbitrary shape means it's other than the straight, then so how to find the force experienced by the conductor? That is, so by dividing the conductor into strips. By dividing the conductor into strips, and we need to find the force experienced by the each strip, and that is the force experienced by the each strip is I into dl bar cross b bar, where dl is the length of the small conductor, small piece of the conductor. The length of the small piece of the conductor is dl bar. Now I into dl bar cross b bar is the force experienced by the each strip, each piece. Now by taking the summation of all the forces in the vector sum of all forces experienced by the all the strips, if you take, then we will get the total force experienced by the conductor. So this is if the conductor is arbitrary shape. So most of the cases generally the sigma is replaced by integral. So if the system is continuous system, then sigma replaced by integration. If the system is discrete system, we use sigma or summation. If the system is continuous system, we use integral. So this is the force experienced by the conductor in external magnetic field. Thank you.